this lesson, we'll focus on solving inequalities, and you can refer back to this cover page at any time. So solving inequalities, it's very, very similar to solving equations. When you solve inequalities, you use inverse operations, you do the same thing to both sides, and you're trying to get your variable alone. But instead of an equal symbol, you have an inequality symbol. So there's one tricky rule, and that is whenever you multiply or divide both sides by a negative, you need to reverse the inequality symbol. Just in this one little situation, whenever you're multiplying or dividing both sides by a negative. And you can check your answer if you're not sure if you should have reversed it or not. You're going to graph your solution on a number line, and you're going to shade the area that makes the inequality true. And just like before, you're going to use an open dot if the boundary is not a solution, because that's not shaded in, so that's not true. Use a closed dot if it is a solution, because that's shading it in, it is true. Let's do some examples. So you're going to solve the inequality and you're going to graph. So really, we do this just like we solve an equation. So we're trying to get x alone, we do the same thing to both sides. So I'm going to subtract 4 from both sides, and then I get 3x on the left, and I get 12 on the right. And then to get x alone, I'm going to divide both sides by 3, and I have x on the left and 4 on the right. But instead of an equation, so I don't have an equal sign, I have this inequality sign. Excuse me. And then you're going to notice that it's a less than symbol. I never multiplied or divided both sides by a negative, so I keep the less than symbol. So I think my answer is x is less than 4. When I graph it, if I put 0 on the number line, I'll put a 4 here. And I have to see, well, is 4 less than 4? It's not, so it gets an open circle. And then I shade the area that makes this true, which should be this stuff over on the left. This is all less than 4. And if you check it, you can check something in that range, like 0 is less than 4. So we can try it in the inequality, like 3 times 0 plus 4. Well, that's just 0 plus 4, or 4. And 4 is less than 16. So likely I did this right. I have the correct side shaded. Okay, let's try another one. So negative 5x minus 2 is less than or equal to 21. I am going to, again, just like I did with an equation, I'm going to try to get x alone. So I add 2 to both sides, and then I have negative 5x, and I have 23. Then I have to divide by negative 5. Now, this doesn't go in evenly, and I usually prefer that you leave it just like as a fraction, and it's common to put negative 23/5. But if you're having trouble interpreting that as a meaning, you could put it in decimal form. It's negative 4.6. And on the left, I have x. Okay, and when I'm checking this, I have to see, did I ever multiply or divide both sides by a negative? Well, right here, notice I divided both sides by negative 5. So what that means is I need to take this inequality symbol and I need to flip it. So it was less than or equal to, so I need to change it to greater than or equal to. So I have x is greater than or equal to negative 23/5, or negative 4.6. When I'm graphing it on a number line, I'm going to put the negative 4.6. Since it's greater than or equal to, it's a solution. I'm going to shade that in, and I'm going to go to the right. And again, when I'm checking, I want to check a place in the boundary, in the shaded area, to see if it works. And 0 is in that again, and 0 is the easiest number to try, so I'm going to try 0. So negative 5 times 0 minus 2, is that less than or equal to 21? Well, that's just 0 minus 2. I have negative 2 is less than or equal to 21. That's true, so it works. All right, let's try a couple more. So again, variables are on both sides. We're going to solve this very normal though. So I like you to get just the variables all together on one side. I would choose to add 4n to both sides just to work with positives. So I have negative 2n plus 4n, that's 2n plus 9. And then the only thing left on the right is the 1. We get n alone, so I'll subtract 9. I just have 2n and negative 8. And then I'm going to divide both sides by 2. If I check, did I ever multiply or divide both sides by a negative? I did not. So when I have n and negative 4, I keep the original symbol, which is a greater than. So n is greater than negative 4. So I'm getting so lucky. I'm always having 0 in my shaded area. So there's -4. There's this. And then we want to check if it works again. So if I plug in 0, on the left side I'll have -2 times 0 plus 9. So that's just 0 plus 9, or 9. On the right side I have -4 times 0 plus 1. 0 plus 1, that's 1. And it has a greater than, so 9 is greater than 1. That's true. So I probably did it right. And the last one, 4 times the quantity 2x minus 7 is greater than or equal to -28. Again, I'm going to simplify my left side of the expression first before I do anything else. So I have 8x minus 28, I use the distributive property, is greater than or equal to -28. Okay, and I'm going to add 28 to both sides. Oh no, some kids get freaked out here. I have a 0 on one side. That's okay, you can have 0 there. So I have 8x and 0. To get x alone, I'm going to divide by 8. And because 0 divided by 8 is just 0, I know it has x and 0. If I look through this problem, I never multiplied or divided both sides by a negative, so I'm going to take this original symbol and keep the greater than or equal to. And so I'm going to plug that in. Greater than or equal to, so 0 is a solution. And I'm going to shade to the right here. This time 0 can't be in my boundary, so let's just try another number like 1. And let's test it out. So I want to know 4 times 2 times 1 minus 7. I want to know if that's greater than or equal to -28. Well, if I do order operations here, 2 times 1 is 2. 2 minus 7 is -5. -5 times 4 is -20. -20 is bigger than -28, so this works.